Okay, welcome back. Now, as I was drawing that last phase of whatever I was drawing, remember I had sodium plus 1 and I had electron and I had this, okay, chlorine and minus 1, right? Right? Now, this is only if you are specifically asked to write the electronic structure or the one with the charge, okay, plus or minus, okay. Conventionally, we all are used to this. So, if I am just asking you for a formula, you don't need to show me all this extra work. This is just the chemical formulae of sodium chloride. If sodium and chlorine were to combine. Okay, now I'm going to give you a couple of compounds, but before that let me just do one more. Let's say, okay, if barium, okay, and chlorine were to combine, okay, these are the two elements that are going to combine. Right away you should know what kind of compound you're dealing with. Well, barium is an alkaline earth metal. So I'm sorry, that was what I meant to say was, it's not what I meant to say. I gave you the answer and that's not good. So what I meant to say was, this is a metal, and what I meant to say was, this is a non-metal. So if you're going to combine a metal and a non-metal, guess what? You're going to have a ionic compound, right? So to make life easy, okay, all we are going to do is to create these formulas like here that you see. You've probably seen a lot of these in chemical compounds and you wonder how they combine, okay. Chemistry, okay, is all about balanced, okay. Now life is never going to be balanced. There's always going to be more of one over the other, but chemistry is all about balanced, which is a term which I want to introduce this moment. Is called stoichiometry, okay. We will deal extensively with this particular word later in the course, but in chemistry you rarely see the word balanced. You see the word stoichiometry or stoichiometric or stoichiometrical ratio. You hear various ways of that particular term, but what really stoichiometry refers to is balanced, okay. Things have to be balanced. Whenever there's so many positive charge, you should somehow manage to get that many negative charge, or if you have so many negative charge, you should somehow find a way to get, or that element would somehow find a way to get that many positive charge, so they are balanced. Balanced sometimes is equal, balanced sometimes means it's balanced, okay. I don't know what other way I can say it. All right, so barium, okay, barium is in group 2A, okay, and chlorine is in group 7A, okay. And so we've already made the connection that the barium is a metal and chlorine is a non-metal. So barium is a alkaline earth metal, so it will lose all of its 2 electrons, so that would lead to barium 2 plus. I have done this earlier and I called it a teaser because I felt that was necessary to talk about this concept back in a past video, but I feel it's also necessary that we talk about it now because this is where it's even more important. So chlorine is a non-metal and it's in group 7A. That means it needs one more to get the magic number of 1 minus. Now, if you keep in mind with the sodium and the chlorine I have here, this is 1 and 1, nothing. You just put them together without making any changes. Now here it's not the same thing. They're not stoichiometrically balanced before they combine, but when a chemical does it on its own, it doesn't need your help, okay. It knows how to does it better than any of us do. But since we are doing it manually ourselves, well, we need to find a way, because there's 2 pluses and 1 minus. Somehow the chlorine should manage itself so that it also gets 2 minus. Now it cannot ever become 2 minus, that is impossible. However, what it can do is instead of having 1 minus, it will have 2 of 1 minus, so that will be 2 minus. Does that make sense? So to get that, all you got to do is move the 2 over here and move the 1 over here. Okay. Now it would look like this: Ba1 Cl2. Now normally in chemistry we don't use 1. 1 does not have any meaning, so we're going to just leave it as BaCl2. Now what it is, like I said, chlorine can never be 2 minus. Okay, this right here, folks, Cl2 minus is not same as 2Cl minus. Okay, this is actually not even possible. Chlorine can never be 2 minus. This is not even possible. Why? Because chlorine is in 7A and it can only take one more electron to get to the magic number of 8. So 2 minus is not even possible. However, 2Cl minus is very much possible. Yeah, why not? I'll take 2 of those. Okay, so it is balanced. Okay, it is not equal, but eventually it became equal. But please do not think that stoichiometry means equal. It means things are in a balanced situation. All right, so let me give you a couple of examples. Okay, so let's do one more. This is all ionic compounds, so let me give you strontium and fluorine. Okay, take a moment, pause the video, and then when you have the right answer, which is the chemical formula, when you combine this metal and a non-metal, continue playing the video and you will find whether or not what you have and what I have is the same. All right, go ahead and pause the video now. All right, so strontium, as we learned, is a metal and fluorine is a non-metal, right? That means when they combine, you are going to generate a ionic compound which will be positive and negatively charged. And metals is usually positive charged, non-metals is usually negatively charged. Strontium is in group 2A, so it will make strontium 2 plus, means it can only lose electrons, and fluorine of course is in 7A, so it will only gain 1 electron. Same rule applies. You cannot ever have F2 minus. So to make it balanced, the 2 goes over here and the 1 goes over here. Let me get a different color. So we will end up with strontium fluoride, and I explained it why we don't write 1, because 1 has no real meaning there. Okay, so this is the name of this is the chemical formula of the compound. Okay, all right, now let's get to covalent compounds. Okay, they are slightly different. All right, so covalent compounds. Okay, what did we say when we talked about covalent compounds? Well, we said that it has to be a combination between non-metal and a non-metal. Okay, now it's important that you pay attention, because it is not as clear cut as ionic compound was. Okay, I am going to take you into something, probably little bit of a jump here, I would say, but I'm cautiously doing this jump, and please bear with me. And this would take us into, in a future, what is called Lewis dot structures. We're not going to get into these right now, but you can call this a teaser, because I want you to understand how I ended up with those structures for oxygen, nitrogen, cyanide, etc. They're called Lewis dot structure, and before that there is also something called valence shell electron pair repulsion theory, VSEPR theory. If you just thought I spoke French, no, I did. I still was speaking English, but I don't expect you to memorize it. It's called valence shell electron pair repulsion theory. All right. So we are not going to get into these. We have dedicated a whole week for this. So I'm going to just take you through the Lewis dot structure as a teaser to understand. Okay. Let's say you're going to combine nitrogen and chlorine. Okay. All right. Or even better, let me do something else actually. Let me do something even more easier. So just to get the idea of it, and as far as covalent compounds, I would test you more of the naming than the compounds itself, at least for week 3, simply because I don't want to teach Lewis dot structure entirely at this context. But you see how even a future concept is tied into a concept that we're learning into the present, and that is exactly the reason why I created those concept maps. Okay. Let's say we're going to combine boron and fluorine. Okay. Unlike ionic compounds where we have to, all we have to do is come up with the charge and then swap the charges and done. But it is not that simple, okay? Because with covalent compounds, they're rarely in equal quantities. One is always going to be more than the other, okay? So if you look at boron, which is a nonmetal as well, and I believe if I bring up the periodic table, okay, it is in 3A, right? Right? It's in 3A, right? Okay. And then you've got your fluorine, which is 7A, right? So you would think that this can accept 5 electrons and this would accept 1 electron. Well, you thought right, but let's bring back the idea of electronegativity. Okay. Okay, electronegativity that we learned, which suggested as you go from left to right in the periodic table in PD, electronegativity, if it's a real class I would probably pause here and have you say this, but since this is a virtual class, electronegativity increases. Okay. Okay, we're not going to actually construct the compound. I guess we can, but what I'm really doing is laying the foundation for Lewis dot structure and how it really ties into the idea of covalent compounds. Okay, people had covalent compounds first and then Lewis dot structure, but it is important. So if you have this combination, well, I don't want to break the surprise, it's already there. If you go to the periodic table, fluorine follows boron, so fluorine is more electronegative of the two. Okay, that means while they're both nonmetals and they both can accept electrons to get to the magic number of 8, well, guess what, mostly it is going to be the fluorine that is going to be the accepting the electrons, but the boron has to donate those electrons. It is just that simple. Okay, let me rephrase it with a different color. While they're both nonmetals, we agree boron is a nonmetal, fluorine is a nonmetal, but we have to apply the electronegativity series, and we notice quickly that fluorine is ahead of boron, and so therefore fluorine is more electronegative compared to fluorine. So between those two, fluorine would accept electrons just like the chlorine was in sodium chloride, and sodium donated electrons. Boron would donate electrons and fluorine would accept those electrons. Okay, so let me give you a compound. Keep those thoughts in mind okay, as we learn these materials. So, this is a compound, boron trifluoride. Okay. I do not expect you to create these, I will just give you these compounds and then have you come up with names for it. Okay. So, if you draw the structure boron, okay, how many valence electrons does it have? How many valence electrons does it have? 3, right? Right? 3a, right? So, that means boron can only, remember we already made our theory right, which is fluorine is more electronegative of the two. So, it would tend to accept electrons, and if you wonder why I am saying that, because I clearly defined electronegativity is the tendency of an atom in an element to accept electrons into its valence orbital. So, we already made the connection that so can donate 3 electrons, okay, and boron is less electronegative of the two, but can it donate as much as it wants? Well, ideally it should be accepting 5, right? But when you make a covalent compound, one has to donate, and how much that one element donates depending on its Roman numeral. So, boron can donate 3, and fluorine, which is in 7a, can only accept 1 electron. That is a pretty predicament situation right there. Can only accept 1 electron. Well, boron will give away its 3 electrons readily, but fluorine can only accept 1. Again, stoichiometry. Fluorine can never accept all 3. Fluorine can only be 1 minus. Boron can only be 3 plus. Okay, you just think of it like an ionic compound business here, but we will not have any charge in the end. Okay, that means we cannot ever have F3 minus. So, again we do the same. So, it is BF3. So, it is kind of like using the ionic compound idea to get to BF3. So, how does this look like? Each boron is giving 1 electron, okay, and each fluorine is accepting 1 electron, right? Right? So, that means each fluorine takes 1 electron from the boron. It does not have to be any particular style. I am just drawing it. Ooh, sorry, the bonds do not bend like that. All right. So, that is let me correct it so you do not carry that notion that bonds can bend, and well, there is a bond bending, but that is really, oops, again I did not do a good job there. But what I am really trying to have you take across is there is that ionic bonding principle which gets contaminated into the covalent compounds, but it is just the analogy, but they have completely different ways of doing things. So, even though they are both non-metals and it leads to a covalent bond, so you see that I did not draw those wedges because this is a purely covalent bond. What this really means is, let me get a different color so I can take this message more strongly. Okay. Unlike the ionic bond, the covalent bond, the electrons are equally shared. Electrons are equally shared. Okay. Now, this is kind of laying foundation to our Lewis structures, which we will later down the road. But then all of a sudden I start talking about a concept like this, you would think, oh, I don't know how you're just making that huge leap. I'm just not able to make that leap. And this is the reason why in the first place I created the concept map, so that I have some kind of a visual structure on how I'm going to go about doing things. So, let us look at one more example if you feel like you're a little bit lost in translation there despite all that explanation. And actually I gave you a lot more explanation than it typically is given. All right. So, let us look at N nitrogen and Cl. Same business. Okay. Nitrogen is if you go back to the periodic table, okay, Now, strictly going by electronegativity, nitrogen is nitrogen is less electronegative than chlorine. So, maybe let us create this compound. Nitrogen and chlorine, it makes a NH. Actually, let us do this. Let us change this to let's change this to something else, because you are probably used to this rather than the other one I really wanted to. Let us do hydrogen. Let me erase this right here, because this is something we are familiar with in the compound that I had in mind. So, electronegativity, we know that this is a nonmetal, and I said hydrogen is not part of the alkali metal column, even though it is there, it is a nonmetal. So, when two nonmetals combine, we are going to have a covalent bond, right? We established that connection, and I don't believe any of you will have that particular problem, because it is quite straightforward. All right. So, now going by the electronegativity, nitrogen is below hydrogen, right? Is that right? So, you would think that hydrogen is more electronegative than nitrogen, right? Well, that is correct, right? So, what do you think will happen? Which of the two elements would more likely donate its electron, and which of the two would accept the electron? You see, you don't want to just learn a concept for the sake of learning it and never ever have to think back at it, and that's usually is the problem when you learn electronegativity. So, that means nitrogen is less Now, if you don't know what I am talking about with electronegativity, obviously you have not watched the video on electronegativity in detail. I recommend you go back and look at it one more time, and what I mentioned for definition and how I went about solving the problem there. Nitrogen is less electronegative than hydrogen. So, nitrogen donates, hydrogen accepts. Now, going back to the same thing. All right, let us open a new screen right here. Nitrogen is 5A. Since it is donating, it does not need to get to the magic number like I mentioned earlier. That means it can donate up to or all 5 electrons, and hydrogen is 1A. Even though it is not part of the alkali metal, it can only accept 1 electron, right? So, if you do the same logic, you would think you will make NH5, right? But if you go back to the periodic table, this is the only exception that you probably will never be able to decode just from the periodic table. It can donate up to, that is why I read it up to. So, let us say if it donates up to 3, that means hydrogen can only accept 1, so 1 minus. Now, we are not looking at a situation, we would look at something else later that where it will use all 5 electrons. But I really want to drive that point that there is a lot of things we learn in the class are associated with our daily life things. It can donate up to 5 or all 5. So, I have just chosen that nitrogen would donate 3 of its electron to hydrogen. That means we swap and then we end up with ammonia. Now, here is the question, hey, what happens to the 2? So, what happened here is each out of the 5 electrons it can donate, nitrogen donated 1 and hydrogen used up its 1 more, and it made these beautiful bonds, right? right? You can ask me what happened to the remaining 2 electrons. Well, they don't do anything, they just sit around. Now these are called lone pair of electrons. Lone pair means lone as in it's loner by itself, and it's paired because there's 2 of them. Okay. Now again, this is more of a teaser. We would learn really all these in great detail, but this is how things relate to. Now ammonia is a common household. It's used in cleaning glasses and stuff like that. Ammonia is very pungent, and it's used in a lot of the household products like cleaning supplies and stuff, household products. Okay, so it can, in both these cases, one of them is a donor and the other is the acceptor. Now ideally you may have never heard anyone see the covalent bond being used +3 1 minus, but I'm purely using that as a way to get my point across. So why you think you have NH3, why not NH5 or something like that? Because I've made it very clear, it doesn't always have to use all 5. It can use up to 2, or it can use up to 5 or 4 and things like that. All right, let's look at one more example before we call this area a quit and then start moving to the idea of. Now let's look at phosphorus and chlorine. Okay, they're both in the same exact row, and phosphorus is a nonmetal and chlorine is a nonmetal. Okay, and chlorine is more electronegative of the 2 because it's ahead of fluorine. So phosphorus would donate, chlorine would accept. Okay, now phosphorus is 5A and chlorine is 7A, right? So which means phosphorus would donate, in this case it can donate all 5, and chlorine would accept all only 1 electron. So that means you would technically have something like P plus 5 and Cl minus 1. So that means you will end up with PCl5 because I'm swapping this. Now we don't typically do this for covalent compounds. Some people might even say on YouTube, oh, you're teaching it wrong. And no, I'm not. I'm just using existing resources and knowledges to drive my point across, and this is not incorrect, just to teach, but you won't really see people doing this. Okay, ideally I will, when we come back to Lewis structures, I would reinforce it. Okay, so this is a covalent compound. Okay, the way it exists is each phosphorus gives 1 electron and the chlorine takes 1 of the electron, and so you'll have 5 single phosphorus and 5 chlorines. Okay. All right. So now we learned about ionic and covalent compounds. The next likely thing to do would be to learn to name them. All right. That will be in a different video.